As night falls and we gaze upon the starry sky, a brilliant band of light stretching across the heavens captures our eyes. Throughout history, this radiant ribbon has inspired countless imaginings and explorations, woven into the mythologies of diverse civilizations as a celestial river or a silvery path. This is our home, the Milky Way galaxy. Yet, this seemingly tranquil band of light is actually a magnificent cosmic island composed of hundreds of billions of stars, vast amounts of interstellar gas and dust, and mysterious dark matter. On an unimaginable scale and complexity, it carries the birth and death of stars, the formation and evolution of planets, and the hidden origins of life itself. Human understanding of the Milky Way has been a long and challenging quest. The story is vast, but before we dive deep into this dreamlike narrative, remember to engage with our journey. From the blurred outlines observed by the naked eye to the countless stars revealed by early telescopes, and finally to the grand structures and dynamics unveiled by modern multi-wavelength astronomy, our understanding has continually deepened. Each breakthrough has pushed the boundaries of our cosmic knowledge. This exploration will lead us through the marvelous journey of the Milky Way, beginning with ancient observations and gradually revealing its structure, birth, evolution, and its unique place within the local group, allowing us to feel the splendor and depth of our cosmic home. The human exploration of the Milky Way began in the distant past. In an era without optical instruments, ancestors viewed that hazy band of light in the night sky as a supernatural presence. Whether it was the heavenly river in Chinese culture or the milk of the goddess Hera in Greek mythology, different civilizations declared this cosmic wonder in their own ways. They observed the patterns of the stars and recorded the changes in the heavens. Although they could not understand the nature of the galaxy, their awe and curiosity were the initial drivers of cosmic exploration. These early observations laid the seeds of astronomy and accumulated precious data for future scientific development. In the early 17th century, the Italian scientist Galileo Galilei pointed his self-made telescope toward the Milky Way, an act that fundamentally changed our perspective. Through the lens, Galileo discovered to his surprise that the blur seen by the naked eye was actually a collection of countless individual stars. This discovery confirmed that the Milky Way was not a cloud of gas but a galaxy composed of a vast number of stars. This was the first time in history that scientific instruments revealed the microscopic structure of the galaxy, marking the transition from naked eye observation to a new era of scientific evidence and laying the foundation for later galactic research. In the late 18th century, William Herschel and his sister Caroline Herschel launched an ambitious census of the stars. They systematically recorded the number of stars in different directions to infer the shape of the Milky Way. Herschel believed the galaxy was a flattened, disk-like structure with the solar system near its center. Although their model had inaccuracies, such as failing to account for how interstellar dust absorbs light, which led to errors in size and the sun's position, Herschel's star counting method was the first attempt at quantitative analysis to describe the macrostructure of the galaxy, providing vital methodology for future galactic mapping. Entering the 20th century, Dutch astronomer Jacobus Kapteyn proposed a more refined model based on precise stellar parallax and motion studies, known as the Kapteyn universe. He still viewed the galaxy as a flat structure with the solar system at its center. While more precise than Herschel's, Kapteyn's work was still limited by interstellar dust blocking the view. However, his work further perfected stellar statistical methods and provided an important framework for deeper research, pushing the boundaries of structural recognition. In the early 20th century, American astronomer Harlow Shapley achieved a breakthrough by studying the distribution of globular clusters. He found that these clusters were not uniformly distributed but concentrated toward the constellation Sagittarius. Shapley reasoned that these clusters orbited the center of the galaxy, which was not where the solar system was located. By measuring the distance to these clusters, Shapley estimated the true size of the Milky Way for the first time and revealed that the Sun is not at its center. This discovery completely overturned the Kapteyn model, removing the solar system from its central status and vastly expanding our understanding of the galaxy's scale and our place within it. Almost simultaneously, Edwin Hubble observed Cepheid variables in the Andromeda Nebula and calculated its distance to be far beyond the Milky Way. This milestone resolved the long-standing great debate, proving that Andromeda was not a gas cloud within our galaxy but a separate, massive galaxy in its own right. Hubble's discovery revealed a universe filled with countless galaxies like our own, expanding the human worldview from a single galaxy to a vast, intergalactic universe. With technological progress, astronomers began using radio and infrared telescopes to further unveil the galaxy's secrets. Because interstellar dust blocks visible light, the galactic center and distant spiral arms were once impossible to observe directly. However, radio waves and infrared light can penetrate this dust, showing us a completely new picture. Radio astronomers used the emissions from neutral hydrogen to map the spiral structure of the Milky Way, revealing its magnificent rotating form. Infrared telescopes allowed us to see the stellar distribution and activity at the galactic center, even detecting the supermassive black hole known as Sagittarius A star hidden deep within. These multi-wavelength observations have greatly enriched our understanding of the galaxy's composition and dynamics. In the 21st century, with the deployment of the Gaia satellite and the James Webb Space Telescope, our observations have reached unprecedented precision. Gaia is dedicated to measuring the positions and motions of billions of stars, building a 3D dynamic map that allows us to study the history of the galaxy and the distribution of dark matter. The James Webb Space Telescope uses its superior infrared capabilities to look through dust into the earliest galaxy formations and the deepest star-forming regions within our own home. The Milky Way is classified as a barred spiral galaxy. Its grand structure consists of several distinct parts including the flat disk, the central bulge, the surrounding halo, and the winding spiral arms. The disk is the most prominent feature, a thin rotating structure where most young stars, gas, and dust are concentrated. Seen from the side, this disk is extremely flat, much like a giant record player spinning slowly in space, containing our solar system and countless others. The central region is the bulge, a dense spherical or elliptical structure. Unlike the young stars in the disk, the bulge consists mostly of older stars with very high density, making this region exceptionally bright. It is one of the oldest parts of the galaxy, where stellar motions are more random and complex. Outside the disk and bulge lies the vast and sparse galactic halo. This nearly spherical structure envelopes the entire galaxy. The halo contains relatively few stars, which are typically very old and low in metal content, moving in random orbits. The halo also hosts many globular clusters, which are dense collections of hundreds of thousands of stars that serve as clues to the galaxy's early history. Most importantly, the halo is thought to be the home of dark matter, a mysterious substance that does not emit light but influences galactic motion through gravity. The galactic disk is not uniform but is composed of several magnificent spiral arms. These are regions of higher density for stars and gas. Current understanding suggests there are 4 major arms, including the Perseus arm and the Scutum Centaurus arm, along with smaller secondary arms. These arms are not fixed physical structures but density waves propagating through the disk, compressing gas to trigger new star formation. Consequently, these arms are the most active birthplaces of stars, filled with bright young stars and nebulae. In terms of size, the Milky Way is a massive structure with a disk diameter of about 100,000 light-years and a thickness of only about 1,000 light-years. Within this vast space, it contains between 100 billion and 400 billion stars, ranging from hot blue giants to cool red dwarfs. Beyond the visible matter, about 85% of the galaxy's mass is made of dark matter. Astronomers discovered this by observing that stars and gas clouds move much faster than can be explained by visible gravity alone. This invisible dark matter halo is crucial to the formation and evolution of the galaxy. Our solar system is located on a secondary arm called the Orion Arm, about 27,000 light-years from the galactic center. This position is ideal, neither too close to the dangerous activity of the center nor too far where heavy elements are scarce. The solar system orbits the galactic center at about 220 kilometers per second, completing one revolution every 240 million years. This stable orbit has provided a consistent environment for the evolution of life on Earth. Stars within the galaxy are divided into different populations. Population 1 stars are relatively young and rich in heavy elements, or metals, primarily found in the disk and spiral arms. Our Sun is a typical population 1 star. In contrast, population 2 stars are the oldest, containing very few metals, and are found in the bulge and halo. They are like living fossils from the early universe, allowing astronomers to trace the galaxy's oldest memories. Between the stars lies the thin interstellar medium, composed of gas and dust. This medium serves as the cradle for new stars. In certain regions, gas and dust gather into dense molecular clouds. Under the influence of gravity, these clouds collapse to form new stars and planetary systems. These molecular clouds are the most active star-forming regions, where low temperatures and high densities allow gravity to overcome gas pressure. As a protostar accumulates matter, its core temperature rises until nuclear fusion begins, birthing a new star that illuminates the surrounding gas to create beautiful nebulae like the Orion Nebula. At the very heart of the Milky Way lies a mysterious place containing a supermassive black hole, Sagittarius A star. With a mass millions of times that of the Sun, it governs the motion of stars in the deepest part of the galaxy. While the black hole itself is invisible, the matter falling into it emits strong radio, infrared, and X-ray signals, providing a unique window into the study of black holes. The birth and evolution of the Milky Way is a story spanning over 10 billion years. It began shortly after the Big Bang when the universe cooled and formed primitive gas clouds. These clouds were not perfectly uniform. Tiny density fluctuations caused higher density regions to attract more matter via gravity. These first collapsing regions are the precursors of galaxies. There are two main theories for how galaxies formed, top-down and bottom-up. The top-down theory suggests large galaxies formed from the collapse of massive original gas clouds, while the bottom-up theory suggests they formed through the merging of many smaller gas clumps. Modern observations favor the bottom-up model, seeing galaxy formation as a continuous process of merging. In the history of the Milky Way, merger events have been vital. Evidence of these mergers exists in the form of stellar streams, remnants of dwarf galaxies torn apart by the Milky Way's gravity. For example, the Sagittarius dwarf spheroidal galaxy has crossed the Milky Way multiple times, leaving behind a magnificent stream of stars. Additionally, tidal tails and the presence of satellite galaxies like the Magellanic Clouds prove that the Milky Way is still interacting with its neighbors, absorbing new gas and stars to continue its growth and evolution across the cosmic timeline. The various components of the Milky Way, the disk, the bulge, and the halo, did not form simultaneously but followed distinct timescales and evolutionary paths. The galactic halo is considered the oldest part of our galaxy, likely formed in the early universe through the merger of many small, primitive galaxies. The stars within these early systems have extremely low metal content, reflecting the pristine chemical composition of the cosmos shortly after its birth. The formation of the central bulge likely occurred during an early period of gravitational collapse, where vast amounts of gas and stars were drawn toward the center by gravity, creating a dense, spherical core. In contrast, the galactic disk formed relatively later. As cosmic gas cooled and fell toward the center of the rotating galaxy, it gradually flattened into a disk-like structure where new generations of stars continue to be born today. The history of star formation in the Milky Way has not been a steady stream but a series of bursts and quiet periods. In the early stages, one or more massive bursts produced the majority of the ancient stars that now inhabit the bulge and the halo. Over time, this activity leveled off, settling primarily into the molecular clouds within the spiral arms. However, galactic mergers can still trigger new star formation. When two galaxies collide, gas clouds are compressed, sparking a new era of stellar birth. By analyzing the distribution of stars of different ages, astronomers can reconstruct this dynamic history and reveal how our galaxy evolved over eons. The chemical evolution of the Milky Way is a continuous process that steadily increases the abundance of heavy elements in the universe. The infant universe contained only hydrogen and helium, the heavier elements necessary for planets and life, such as carbon, oxygen, and iron, were forged deep inside stars through nuclear fusion. When massive stars exhaust their fuel and end their lives in spectacular supernova explosions, they scatter these heavy elements into interstellar space. This enriched material is later pulled into new star-forming regions, becoming part of the next generation of stars and planets. Consequently, younger stars generally have higher metal content, which explains why population 1 stars are richer in heavy elements than the ancient population 2 stars. This chemical enrichment provided the essential building blocks for the eventual emergence of life on Earth. The future of the Milky Way is also destined for change as it prepares for a magnificent cosmic collision with the Andromeda Galaxy, the largest member of our local group. Currently, Andromeda is racing toward us at about 110 kilometers per second. While a collision sounds catastrophic, the vast distances between individual stars mean that direct stellar impacts are highly unlikely. Instead, the two galaxies will pass through each other, their mutual gravity reshaping their forms over billions of years until they merge into a single, massive elliptical galaxy often referred to as Milky. This merger will be one of the most spectacular events in the history of our galactic home. In the vastness of the universe, the search for life is an eternal human pursuit, and the concept of the galactic habitable zone is a crucial theory in this quest. This refers to the specific regions within the Milky Way where environmental conditions are stable enough for complex life to exist and evolve over long periods. Defining this zone involves more than just distance from the center, it requires a balance of radiation levels, the frequency of nearby supernovas, the abundance of heavy elements, and the stability of stellar orbits. The inner boundary of this habitable zone is restricted by the extreme environment near the galactic center, where the supermassive black hole Sagittarius A star and a high density of stars create intense radiation. Frequent supernovas and gravitational perturbations in the crowded center would make planetary orbits unstable and threaten any biological life with lethal X-rays and gamma rays. Conversely, the outer boundary is limited by a lack of heavy elements. In the sparsely populated outer reaches of the galaxy, there is not enough carbon, silicon, or iron to form rocky, Earth-like planets. Therefore, the abundance of these elements acts as a natural limit to where life can thrive. Our solar system is perfectly situated in a cosmic oasis about 27,000 light-years from the center. This location is far enough away from the dangerous radiation of the core but close enough to have sufficient heavy elements for planet building. Furthermore, the Sun follows a nearly circular orbit, which allows us to stay within a stable and quiet environment, avoiding the chaotic spiral arms or dangerous close encounters with other stars. The type of star also matters. Our Sun is a G-type main sequence star, which is ideal because it lives for billions of years, long enough for life to evolve, and maintains a very stable light output. While smaller M-dwarf stars are more common and live much longer, their planets often face challenges like tidal locking or intense solar flares. Despite these complexities, our understanding of habitability continues to grow. Future space telescopes like the James Webb will allow us to analyze the atmospheres of distant worlds, searching for the chemical signatures of life and revealing the true biological potential of the Milky Way. The Milky Way does not exist in isolation, it is part of a larger collection of galaxies called the Local Group. This gravitationally bound system spans about 10 million light-years and contains three main members: the Milky Way, Andromeda, and the Triangulum galaxy, along with over 50 smaller dwarf galaxies. Andromeda, or M31, is the largest, containing perhaps 1 trillion stars and spanning over 200,000 light-years. The Triangulum galaxy, or M33, is the third largest and is the only other spiral galaxy in the group visible to the naked eye under dark skies. Surrounding these giants are numerous dwarf galaxies, such as the Large and Small Magellanic Clouds, which act as satellites orbiting the Milky Way. These small systems are like living fossils of the early universe, helping us understand how larger galaxies are built through continuous accretion. Within the Local Group, galaxies are constantly tugging on one another. The eventual merger of the Milky Way and Andromeda will transform the group's dynamic, eventually leaving a single giant elliptical galaxy at its heart. The Local Group itself is just a tiny part of a much larger cosmic web. We are situated on the outskirts of the Virgo supercluster, a massive structure containing thousands of galaxies. This hierarchical organization of the universe shows how gravity has shaped the cosmos from tiny initial fluctuations into a grand network of clusters and filaments. Looking up at the radiant band of the Milky Way, we see more than just light. We see a saga of discovery that stretches from ancient myths to the cutting edge of modern science. From Galileo's first glimpse of individual stars to our current mapping of dark matter, each step has deepened our connection to the cosmos. The Milky Way is a living laboratory where stars are born and die, recycling the elements of life. As we continue to explore the mysteries of dark matter, the mechanics of our central black hole, and the potential for life on other worlds, we are reminded of our own smallness and the miracle of our existence. This curiosity and thirst for truth are the very sources of human progress. May we always maintain our sense of wonder for the stars and continue to write the brilliant chapter of human exploration. That concludes our journey for today. May you have beautiful dreams and a wonderful day ahead. Until next time.